and we're going to be talking today about 3D into what has up till now been primarily a 2D API, and that is JavaFX. So we'll go ahead and get started with our presentation. So what I'll do is, if there are any questions on a particular section or topic, I'll take a few during the middle, but I'd rather have most questions wait until the end. But if you have a clarifying question on something that is very specific to the topic we're covering, go ahead and ask it then. But I'll plan to leave plenty of time, probably 15 minutes or at least 10 at the end for questions. So, all right, go ahead. The lawyers made us put this on here, so be sure to read that. Go ahead. The agenda that I'd like to go over today, some of you may have attended the talk that we did last year. The first couple of sections are, I'm going to go over them a little more quickly than I did last year, so, but it will be somewhat of a refresher for those who saw it last year, and it'll be new for those who haven't. And that's that we want to go over a little bit of an overview on JavaFX graphics. We want to go over the transform model of JavaFX, and then talk about cameras and the coordinate system, things that now become important as we're doing 3D. And then talk about things like depth testing, and some of the things we're adding in JavaFX 8 are movable cameras, 3D geometry and attributes, and we'll get into those a little bit later. Okay, next slide. So for those of you, so first of all, how many of you have programmed in JavaFX before? Let's see by the show of hands. Okay, so a good number of you have. So yes, I suspect you have, Carol. Thanks. A lot of people, when they first get into it, find out that it's a different model, especially if you come from the world of Swing or just doing straight Java 2D programming. JavaFX is fundamentally a scene graph-based API. That means you define things in terms of a scene graph hierarchy with transforms to position objects relative to one another. We have two different types of nodes in JavaFX. We have group nodes or parent nodes. Those have children but no direct geometry. And then at the leaf of our scene graph, we have the geometric primitives. The parent-child relationship is a directed acyclic graph, for those of you who are familiar with that. All right, go ahead. And some of the capabilities that the scene graph provides. Every node in the scene graph has a transform, and we'll talk more about that in detail. We have provided animation in JavaFX to allow you to very easily animate over time any number of properties, whether it be a transform, a color, or just some data value that you want to use. You can apply an animation to that, and it will automatically interpolate those values over time. We have a number of different 2D filter effects like blurs, drop shadows, color filters, motion blur, various other effects. And then we have a number of rendering attributes that you can apply to your scene graph objects. Next slide. So the primary graphical nodes that we have, there's really three types. Actually four if we count image and media separate. So we have basic shapes like rectangles, ellipses, general paths, and then we have text, which is, although it inherits shape, it's a very specialized rendering. So we have fonts and various types of anti-aliasing that you can apply to text nodes. It also does text layout so that it will wrap in a text field object, or on a web page with our MeshView component, it will wrap text appropriately as a browser would. And then the other two types of nodes we have are very similar to one another, and that's we have an ability to view an image or a media stream as a node in the scene graph. Okay, next slide. So this is a block diagram of the JavaFX software structure, I guess you'd call it. The application sees the JavaFX UI controls and the scene graph API. Underneath the JavaFX scene graph API, we have the Prism renderer. That's the rendering engine that we use to render all JavaFX primitives. We have two main hardware accelerated pipelines, one for Direct3D, which we use on Windows, and one for OpenGL, which we use on all other platforms, including, if any of you saw the keynote or have seen the kiosks around, we now run on Linux ARM platforms, and all that's done using OpenGL. On the smaller devices, we use OpenGL ES. On desktop devices, we just use standard OpenGL GL2, although we stick primarily to the ES2 subset. In addition, you'll see over on the right a third pipeline, the software pipeline. When we're running on devices that either don't have the proper hardware support or whose driver is too old, or we haven't managed to qualify and make it robust, we will run in the software pipeline case. Usually for Windows, it's only if you're running on older hardware. So we require Intel HD or better on Intel devices and a reasonably modern NVIDIA or ATI hardware. And similarly on Mac and Linux. And we'll have a slide on that in a minute so that you know where you're going to get hardware acceleration. We will automatically detect and fall back to software if we need to. Okay, next slide. So this is a simple scene graph for those of you who haven't seen JavaFX before. It's brand new to you, and for those that have, it's a refresher. A stage is the JavaFX equivalent of a window. So it's a top-level window that you create, and it can run either in a browser or on the desktop unchanged. So you just create a JavaFX stage, and it can either be embedded in a browser, or we will create a top-level frame for you and then render that. A scene is the content of your stage. So you can almost think of that. The analogy in Swing might be the content pane that you would put in. And then a scene has a background color. So in this case, this is an example that we'll show you in code as well. So we're going to put a silver background color on the scene, and that will fill the entire scene, which is sized to fit the visible drawing area of the stage. Then we have a root node, which is just the root of your graph. And in this case, it's just a simple group node. And then finally, we have a single leaf node, which is an image view. And we will load in an image, apply a drop shadow, and then position it in the window. Okay, why don't we go ahead and go to the next slide. Oh, yeah, go to the next slide first. Sorry. Okay, we are ready then. So go ahead and switch to the demo now. So we're going to run the first few programs in NetBeans, and we'll show you some code samples for some of these. Hope you can see back there in the back row. Sorry, we can't make the font any bigger. But what we have here is just the most straightforward JavaFX program. The entire program is actually shown on the screen right there. That's the whole thing, excluding the import statements that you need to make those classes known to Java. So we first start out by defining a subclass of JavaFX application. All JavaFX applications are defined that way, and they have a start method that you must override. We pass in a stage into that start method. The JavaFX runtime does, and that's the primary stage that your application has at its disposal. And so what our application does, our subclass, which is called simple, which is a pretty basic application, is we will set the title of that stage. We will create a scene and then assign it a color. And then we will create an image, and to do that we just specify a URL, and that will create an image object, and from that we create an image view node, apply a drop shadow effect, and then position it on the scene. Because we don't have any other transforms, that coordinate 250, 250 will be relative to the upper left-hand corner of the scene. All right, why don't we go ahead and run that program. So, not a very exciting program, but it does just what the program shows. It loads in an image and positions it with a drop shadow. So that's your simplest JavaFX program, and you could actually take that program, compile it, and run it with no trouble. All right, go ahead. Let's go back to the slides. Next slide. Okay, so we started to touch on the notion of transforms. When you get to 3D, it becomes even more important, but even for 2D, transforms are the way you take nodes and position it relative to each other. So in our previous example, what we did is we took that image view, applied a transform to it in both X and Y to position it in the appropriate place on the screen. So some of the various properties on Node that allow you to do different transform operations are the layout X and Y properties. Those are actually reserved for the layout manager. If you put this in a layout container, such as a flow pane or an H box or a V box or any of a number of other built-in layout containers or ones that you write, it will modify the layout X and layout Y of every node underneath that. So the only time you as an application developer should ever use layout X and Y is if you're doing your own layout and not putting it in a layout container. So that's sort of for whoever is the layout manager to do a final positioning of that relative to its parent. And then we also have a translate X and Y, and if you'll notice in red we've highlighted translate Z. That's actually in the API today. So even though we don't have 3D geometry, we do have 3D transforms today, and they've been in since JavaFX 2.0. And so you can translate or position your node in X and Y or in Z, so you can push it forward or pull it back in terms of its relative closeness to the viewer. Similarly, we have rotation and scale operations. The rotation angle by default is just a 2D rotation. It rotates about the Z-axis, which is just a line going straight through the center of your object. And that's what it will rotate around. But you can specify a different axis, and we'll show a few examples of that, where you can rotate an object in Y, and so it will spin around like this. Or you can rotate it about X, in which case it'll spin around the horizontal axis. Or you can define your own axis with any 3D vector. Likewise, we have scales, separate scale values for X, Y, and Z. You can scale them uniformly by binding those three to the same property, and then you'll get a uniform scale, or you can distort it in X and Y or Z and scale them independently. Finally, we have, for those applications that want a little more control, an arbitrary list of transform objects. And so every node has those first few, we call them convenience transforms. And a lot of our built-in interpolators, animators, will operate on those. Or you can just roll your own and set an array of transforms. Okay, next slide. So the transform objects that can make up that array of objects are made up of either translate, scale, or rotate. We also have a general purpose affine, but that's a more advanced topic than we want to get into today. All right, go ahead for next slide. It's important to understand what the order of transforms are. So the way we apply transforms in a node is similar to how we apply them going down the hierarchy from node to node. So if you have a parent node with some transforms, they're applied first, and then you have a child node that might have its own transforms, then they're applied next. Within each node, they're applied in this following order. The layout and translate X and Y and the translate Z are applied first. And then finally, and then we apply a pivot transform so that we will do our rotations and scales about the center of the object. And then we do the rotation and scale. And then finally we undo the pivot so that we put it back. So basically what that does is it allows you to rotate the object independently from translation. And then finally we apply the list of all transform objects in order from 0 through n, where n is the number of transforms you have. All right, go ahead, next slide. So one of the things that's unique about 3D that you don't encounter in 2D is the need to have the objects sorted based on where they are relative to the viewer. In 2D, the Z order is strictly defined by the render order. So if you define 5 nodes, A, B, C, D, and E, they will be rendered A first, so it'll be on the bottom, then B, then C, then D, and lastly E, which will be rendered on the top. And that's always the way it works in 2D. Next slide, please. In fact, this is an illustration of that with 4 nodes. I might have a root node, a couple of groups, and then 4 different leaf nodes. So for the 4 children, A, B, C, and D, will be rendered in that order with A on the bottom and D on the top. Next slide. So the render order for 3D objects doesn't necessarily correspond to what the Z depth of those objects are. If you apply different transforms, or if you have completely different group nodes with different Z values, you might have a case where you have a very different rendering order. So if you go to the next slide. In this same case, imagine that we have a z-translate value such that the z-values are shown with the object A being at z equals 0, object B at 3, and so on. In this case, the rendering order hasn't changed. It's still A, B, C, and D. And that's the order they're going to be rendered. And so D will be on top. However, if you go based on the Z orders, A should be on top, followed by C, D, and then B. So we really would like to render B first, and then D, then C, then A, but we can't do that without reorganizing our scene graph. But we have a different solution for that, and 3D graphics cards will support this different solution, and that's called a Z buffer. So if we go ahead to the next slide. A Z buffer or depth buffer is part of OpenGL and DirectX, and all 3D hardware will support this. And what it does is a per pixel sort based on the Z value of that pixel. So if you draw 4 rectangles as we showed above, then regardless of what order you draw them in, the one with the Z value closest to the viewer will always appear as if it was on top, whether it was drawn first, last, or somewhere in the middle. Okay? So in JavaFX, we've provided control for the Z buffer by allowing you to construct a scene with or without a Z buffer. The default is without, because most 2D applications not only don't want a Z buffer, it would actually be harmful. And so we allow you to specify a depth buffer, or the request to create a depth buffer in the constructor of the scene object. And then each node lets you decide whether or not you're going to use the Z buffer. So there's a depth test property on every node. It has 3 values, and by default it inherits from its parent. And so the root node by default will inherit from the scene. So only if the scene has requested a Z buffer will you get Z buffering, and then if you request it, you'll get it by default on everything. But you can turn it on and off as needed. Okay, go ahead. So now that we've discussed our first 3D feature, it's time for me to point out that 3D is an optional feature in JavaFX. So if you remember back, we talked about the 3 pipelines. There's the 2 hardware-accelerated pipelines, Direct3D and OpenGL, and then there's the software unaccelerated pipeline. Currently, the software pipeline does not support 3D. It is also possible that we might someday put JavaFX, even with hardware support, on a device that, for whatever reason, doesn't support 3D or whose driver is incapable of doing it. So we've made 3D an optional feature. It's always in the API, but you have to query it if you want to be sure that it's actually going to be there at runtime. And the way we provide that is by having a conditional feature, and that's scene 3D is the conditional feature bit that you would check. And that indicates that 3D is available on the platform, which means a whole bunch of things. It means your perspective camera, which we'll talk about in a minute, is available. It means your depth buffer is going to be available. And it means our 3D geometry, which we'll talk about later, is available. So in the absence of this, you can't reliably use 3D. Okay, next slide. So on Windows, I alluded to this earlier, we use Direct3D. We require version 9.0c, which is actually very old by now, so we don't have a very high requirement on our software version. But we do require pixel shader level 3, and so with the driver support that we need, we really need on Intel HD or higher. So there are some older laptops around that are going to have Intels that are pre-HD. We don't run hardware accelerated on those. We'll fall back to software. And pretty much any modern NVIDIA or ATI can support it. Okay. On Mac OS X, pretty much any modern hardware, in fact, anything that supports Mountain Lion will run Prism. Most things that support Lion, although Apple doesn't check, so you can actually run it on older hardware, but anything on the hardware configuration list of Lion-supported systems will also be able to run Prism in hardware accelerated mode. Okay. Oh, sorry, please. Yes.
But you said earlier that software pipeline doesn't support.
That's right. So if we detect a platform that doesn't support hardware accelerated, we will fall back to the software pipeline, and in that case, if you query conditional feature scene 3D, it will return false.
So fall back to software.
No, well, fallback to software means you don't have 3D, absolutely. Okay, yeah. Yeah, to make that clear, fallback to software is for everything else you would do in JavaFX. So you still have 2D transforms, you still have effects, you still have the ability to draw into a canvas. You don't have 3D. That's very true. Okay, go ahead. On Linux, our story is a little bit evolving, and that's because the driver support on Linux is spotty at best. As of the time we did JavaFX 2.2, really only NVIDIA had decent enough drivers that we felt it worth our time to qualify it. Every time we tried running on Intel, it was an exercise in pain. And on ATI, we just didn't have time to qualify it. And on our main platform, which is Ubuntu 10.04, for our current version, there was really no good ATI driver support. For our next version, which is FX8, which will be releasing with JDK 8, we plan to qualify ATI drivers. And ATI now has reasonably good driver support for Ubuntu 12.04 LTS, which is going to be what we're going to spec out for anybody wanting to use 3D. All right, go ahead. Okay, so since we were talking about depth testing, we thought it would be a good idea to show you a demo of what depth testing is and why you need it. So if you want to, we'll go through the slides, or the code first. So the first thing to notice is we are going to create 3 rectangles and do pretty much what I showed you in that sample scene graph. We're going to have it such that the Z order is different from the rendering order. And so if you look, we're creating a green, a red, a green, and a blue rectangle. The blue rectangle should be in the middle. The red rectangle should be in front. And the green rectangle should be at the back. But that's not the order they're drawn. So in the absence of a Z buffer, it's going to appear as if the blue rectangle is always on top. Okay, why don't you go ahead and run the program. So sure enough, there it comes up, and even before you move it, you can see that the blue rectangle, even though it should be in the middle, is on top. Now what happens if you rotate it about the y-axis? So you can see it looks like it's supposed to be in the middle, and then you rotate it, breaks the illusion because now it's back on top again, the blue rectangle. So the solution, again, is to request a Z buffer. The reason this happened is because we just created a default scene. We didn't request a Z buffer. So why don't we go ahead and do that? So if you look at that line of code there on the screen, so we comment out the, or I guess uncomment the new one. You need to, no, wrong one, up, there you go. So we need to comment out the old creation of the scene, and then we create a scene with the depth buffer flag set to true. Now go ahead and run it again. So in this case, correctly now, blue is in the middle, regardless, and then red and green are correctly in front and back as they rotate around each other. And so go ahead and rotate it again. Yes?
It seems like we are looking into positives and negatives.
Yes, we are. We'll get to that in a minute. Thanks for the question. Yes, absolutely. Well, we've got a slide on that, but Z goes positive into the screen. So now, if we wanted to disable Z buffering, we can do that. So this will disable it on the rotation group that actually has the 3 rectangles. And so now we're back no better than we were before because we've turned Z buffering on and off. Okay, all right, go ahead. And then we can run the next program. So the next one, we won't show you source code for this because it's creating a cube out of 6 2D objects and 6 transforms and positions. And so that the code isn't really what we wanted to illustrate here. This just shows you what you can do, even with the existing API. So this is possible with JavaFX 2.2 today. And if you expand it, you can see that this really is, this is just 6 separate faces, each of which has a media view on it. Now, if you turn off depth buffering, put it back to the Y rotation. Thanks. Okay, so if you turn on depth buffering and then expand it and collapse it again, you can see you just don't get a very realistic. That does not now feel like a solid object because it isn't. Now, if you turn depth buffering back on, you get the solid effect again. So this is why depth buffering is so important, because in the absence of depth buffering, we would have to reorder those 6 faces every frame. Well, if all you had is 6 faces in your scene, that's not that big a deal. But if you have hundreds or thousands of those cubes with 6 faces, or if you have spheres or other things more, it's just not practical. I'm sorry, yes, you had a question? We don't, but there's no reason why at least a couple of these, like, so this one we couldn't post the media because we don't have the rights to ship it. We have the rights only to show it. We do have, so we do have one that shows a 3D cube like this. Do you want to run the color cube? So are you familiar with the ensemble sample? So that's our primary sample. It's maybe if we have time, we'll run it at the end. I'm not sure we will, but we'll be showing that at the booth. It's a demo that shows a collection of individual samples, one of which is the color cube that you're seeing here. That one is available online, absolutely. You just go to the main download site for Java SE, and if you go to the demos and samples, it will be there. So if you just download JavaFX samples and look at the color cube sample inside there. And Ensemble, if you also look at the code, Ensemble has the check for whether or not Scene 3D is supported. And so if you run that on a Linux machine with an Intel card, and go to the Cube 3D sample, it'll just say, I'm sorry, you can't run 3D. So it's got that, yes? The transforms will not work correctly. So what's documented to happen and what actually happens are ever so slightly different. It's documented that the transform will be an identity if it has any 3D. So if you do anything other than a scale, translate, or rotate about the z-axis, anything other than a 2D transform, we say, oh, we're just going to treat that as the identity. What we actually do is treat it as sort of we use the 2D portion of that, because we're just going to end up doing the math anyway and then projecting it without perspective, without camera. So it doesn't give you a very happy experience. What we would like to do is do something a little more consistent, and we're going to have to, so for the 3D primitives, we need to do something better than that. I think in that case we're just going to say it doesn't draw at all, because there is nothing really sensible we can do in that case, until we have software support for that. Okay, next slide. Yeah, we already did the video cube demo. Okay, so we touched a little bit, and then Carol's question kind of highlighted the fact that we have to talk about the coordinate system of JavaFX. So we have a camera in JavaFX, and what that is an object that says how you're supposed to view your scene. Well, in 2D, there really isn't much of a concept of a camera. In 3D, we have 2 different types of cameras that we can use. One of them is a parallel camera, which actually mimics exactly what a 2D viewing would be. And that's the default. It's a viewing volume for an orthographic projection, and it's basically just a rectangular viewing area that you're going to get whatever is in that rectangular area rendered onto your window. The units are in pixel coordinates by default, and the origin is in the upper left corner of the window. So for those of you familiar with either window system programming directly or with Swing or anything else, this will be very familiar to you. Go ahead, next slide. We also have a perspective camera, which you have to create and select explicitly. By default, if you use the fixed camera, which is all we have in JavaFX 2.2, you could switch between a perspective camera and a parallel camera, and you will see nothing different as long as you don't have 3D transforms. So for objects at z equals 0 in scene coordinates, they look the same. So independent of whether or not you have perspective or parallel. We have a field of view property, which for any of you who are familiar with real cameras, it mimics a field of view. You know, it just says how wide an angle you have on your camera. The fixed camera that we have defined right now is located at the center of the scene, and it looks along the positive z-axis. So we have x going to the left, y going down, and z going into the screen. And again, the units by default are in pixel coordinates because we didn't want 2D users to have to change everything they do just because you did a perspective camera. Next slide. So for those of you who have done a lot of 3D programming, there's a few differences. Most people tend to think of 0, 0 in the center when you're doing 3D, just because it's a lot easier to model things that way. Very often your units will not be pixel coordinates. They will either be some units like meters or centimeters or miles or parsecs or maybe even some normalized coordinate system like just a -1 to 1 space. And so you want to be able to handle that. Well, we provide 3D transforms in each of our nodes to allow you to handle that. Also, a lot of times we have a direction associated with your model. So if you load a model, it might be upside down if that modeler expected that Y was up. So it's just a simple matter to flip your object the other way, because JavaFX's camera always goes Y down and always goes Z into the screen. All right, next slide. So one of the things you could do, this is just an example of something. We're currently not planning to provide a utility directly to do this, although we will provide sample code to do it. And it's something we could someday provide an ease of use utility. And that's that you could provide a simple coordinate system converter group up at the top of your scene graph, your 3D portion of your scene graph. And then, so we're going to show an example of doing just that, where we have a translate, rotate, and scale that we can apply to turn things around and put them in the center. And then we're going to show that by having an X, Y, and a Z axis, and then a box that we're going to put in there. Yes? So today, a scene can only have one camera. That's something, good question, and we'll cover that. We've added the ability to have scene within a scene, but the main scene that's drawn on the window is drawn with a single camera. So you can switch between them, but for any one rendering frame, there's only one camera per scene, with an exception that I'll talk about a little later. All right, go ahead. And then I think we'll go ahead, without that or any further ado, we'll run the coordinate system demo. So this is just something, we actually did this for last year's talk as a way to introduce coordinate systems, and I think it's important enough to run through it. And so if you want to run the application, I don't think there's much in the, oh, actually there's one thing I wanted to highlight is note that we have explicitly set a perspective camera as well as turned Z buffering on by creating the scene with a Z buffer. Okay. Okay, so here, by default, if you just create an X, Y, and a Z axis lines, it'll show up in the upper left-hand corner. That's where 0, 0, 0 is, in the absence of any other transforms. Okay, go ahead and add an object. So now we're going to add our image view. But the modeler of this 3D cube of images thought that Y should be going up, and so that's why it's upside down. So now we could translate that. So with our coordinate system group, we can translate that into the center. Now you can move it around a little bit if you want. And then reset that, and then, but we're still upside down. So now you can turn that right side up. And now you can still move it around. Okay, so, and you'll notice Z buffering is on, and you can turn that off, but we've already done that, so yeah, you can see that. So that's how our camera works today. It's a fixed camera, so the camera does not move. In this case, what we're doing is we're moving the object only. All right, go ahead and go back to the slides. Okay. Yeah, in that case, we're moving the group. That's correct. In fact, that chord sys helper group is what we're moving. Yes? Are you using the matrix operation now, no, in that one we're using separate ones for translating it to the center and rotating it about there. The mouse controller, I can't remember what we used. That one might be an affine, or it might have been 3 separate ones. You could do it either way. All right, well, that's probably better. Okay, so here are some of the features now that we're talking about that are going to be coming in FX8, which, as I mentioned earlier, is going to be part of JDK8. So that's under development now. Early access builds of FX8 are available with with JDK 8, but we don't have any of the stuff we're now talking about is under development right now. So anything we show you from here on out is a prototype of what we will eventually have, and so any code snippets we have will be in slides. So what we're adding is movable cameras. So you saw the fixed cameras. We're going to move them now. We've got various 3D primitives, 3D attributes, and then we're adding a few other auxiliary functions like 3D picking. Okay. So this is our class hierarchy. Today, camera inherits from object. It's not a node in the scene graph. What we're changing is that camera is now going to inherit from node. What that allows you to do is stick it in the scene graph as a node in the graph and thereby position it along with everything else in your scene graph. So the position and orientation of that camera will inherit from whatever transforms that it has in the scene. We're also adding a subscene. So that gets to the question of how do you have multiple cameras? And we'll talk about that in a minute. Go ahead, next slide. So I think we pretty much touched on this already. I want to point out, though, for backward compatibility, if all you have is a fixed camera, you don't need to add it as a node in the graph. You still, in all cases, you say scene.set camera. That's the way you tell the scene to use the camera, to render. But you don't have to add the camera as a node anywhere in your scene graph if you don't want to. That's only needed if you're going to move it. We also are adding new properties for near and far clipping plane to control the Z buffer range better. Okay? And this is the code that you saw in the other slide. It's very straightforward, and that's all you have to do to add a camera to the scene. Now, if you want to move it, the new code, so the first code in gray there is the same as the previous slide. That doesn't change. But if you want to move the camera, in this case, I decided I wanted to create a group on top of the camera just to illustrate that you can move the camera or any of its parents in the scene graph hierarchy. So in this case, I create a group. I add the camera as a child of that group and add the group as a child of the root node. And now I can, using transforms, rotate either the camera or the group node that camera is a member of. And in either case, that moves the camera and moves what you will see. Okay, next slide. So SubScene is the way that you can have different parts of your scene rendered with different cameras. There are many uses of this. There's like a rear view mirror or picture in a picture type of an application. One of the main uses, though, that we expect to be used is that you can have your 2D content unaffected by your movable camera, because that would be rather disconcerting. If you wanted a straight overlay of UI controls and didn't want them to start flipping around and moving every time you moved your camera, SubScene is the way you would do that. Okay. All right, so we'll now go to a movable camera demo. Okay, so here what we have is 3 axes. Again, they're the X and Y are all you can see because Z is going straight into the screen. Oh, now you can see the Z. And now if you move the object, you'll notice in this case, because I've attached the coordinate system as a representation of the actual camera's coordinate system, it doesn't move when we move the object. But we can move the camera too now. So with the other control that he's using, he's actually transforming the camera by changing the transforms above that camera. So one of the other things you'll notice is you see those buttons up there. That's an example of using SubScene. So those buttons are not moving when he's moving the camera, and they form an overlay that are always drawn on top of the object. And as you move up there, we'll be able to see that. So just move it up a little bit more. Move that up so that it goes above. Get it up to there. There we go. Okay, so even though those 2D controls are not being Z buffered, they're not positioned using that camera, but they appear as an overlay, and that's done with SubScene. Okay, why don't we go back to the slides. Okay, so 3D geometry. Everything that we've shown, including that last example, is done exclusively with 2D shapes. Image views, rectangles, circles. All we've been doing that's been 3D has been the transforms and the camera. So what we're adding in FX8 is real 3D geometry. And we're doing two flavors of 3D geometry. Either you define your own mesh, your own surface with whatever mathematical equation or model that you have created, or you can use three predefined shapes that we have defined. Go ahead to the next slide. So MeshView is the way you define your own geometry, and then those are the other three shapes. They inherit from a new abstract base class called Shape3D, which is analogous to the 2D shape class. Okay, next slide. And then a MeshView object takes a mesh data component, which defines the actual geometry. And right now we provide one concrete class, triangle mesh. Next slide. So the triangle mesh is defined as a set of positions and texture coordinates. Those are the vertexes that are in your object. And the faces define the topology. So you would define the faces as a list of positions and a list of texture coordinates that make up each triangle in your mesh. We've introduced the concept of smoothing groups. For any of you who are 3D modelers, you'll recognize it, and any that aren't, we'll show you an example later on. It's basically defining which parts of your mesh should be treated as a continuous curved surface and which ones should be considered discrete facets and so should have a hard edge between them. Important to note that a single mesh can be shared among any number of MeshView objects in the same way that a single image or media can be shared among any number of ImageView or MediaView objects. Okay, go ahead. To define a mesh view, you would create an array of positions and texture coordinates, and we won't show that. That's beyond the scope of this talk to say how you're going to do that. And then you would create your list of faces, which are just, as I mentioned earlier, indices into the text chords and positions. And then finally, you create your mesh object by setting the positions, text chords, and faces arrays, and then create your mesh view node. And so mesh view is the thing that's a node in the scene graph and can go in anywhere any other node can go in. Okay, so let's... Okay, this is a mesh view object. You can move it around. Doesn't look much like a 3D object, but if you turn it into wireframe, you'll see it's made up of lots of tiny little lines. You can turn it back into solid. Because it's a bunch of individual vertices, we can apply different operations. We can change those vertices on the fly, and we can actually make it into a function. Any mathematical function we want, we can define that. Now you can move that around. And so if you rotate that, you'll see that it has some lighting that's playing off that and some material attributes. So we'll talk about those later. Okay, so let's move on to the next one. Next slide. Yeah, but next slide. Yeah, we have slides on that. No, it's okay. Okay, and then just really quickly, using the predefined shapes, we've defined sphere, cylinder, and box. You specify a sphere. It's as simple as that first constructor. You just give it a radius, and we'll do a default tessellation on that. So unlike 2D circles or ellipses, these are actually converted into a mesh view. So we will either use a default tessellation into a mesh view, and we'll show you that in a bit, or you can specify it. And then similarly, a cylinder and box. All right, go ahead to the next slide. Now let's run the demo. Okay, in this case, we're going to show one of the three predefined solids. That's a cylinder. And so getting back to the concept of smoothing group, the top and the bottom are in a different smoothing group than the body of the sphere, because the body of the sphere is one continuous curved surface, but there's a hard edge between the body and each of the top and the bottom. So that's what smoothing groups are used for. And then if you turn it to wireframe, you can see that we really do tessellate this into a mesh. And you can create a higher res version of this if we want. And that just shows you how it's tessellated. If you turn it back to solid, you'll see go to the lower res version. You may not be able to see it as well from the back row, but you can actually see that it's more faceted this way than this way, and that's what you would control with the tessellation. All right, let's show the other primitives really quickly. So we've got sphere, and then we've got a box. All right, let's move on. We're going to talk about materials next. So far we've not talked about anything other than the geometry, but there's also different attributes. We've got lighting and materials. Materials are used to specify the appearance of the shape. Lights are used to define the environmental lighting that would go on, similar to the way you'd use lights in a photo shoot. We have a couple of other various attributes like culling and wireframe mode, which we showed the wireframe mode earlier. All right, go ahead. So lights inherit from a single base class called light base, and then we have two types defined now, ambient and point. We might consider additional types of light in the future. Those are the only two we're committing to for this release. Okay. Lights are also nodes in the scene graph, just like cameras. We have a default light if you don't specify one. But as soon as you add a light to the scene graph, that now becomes your light, and we'll remove the default light automatically. Each light can affect either the whole scene graph or just a portion of the scene graph. By default, it affects the whole scene graph. You can specify a list of usually group nodes to define portions of your model that get affected by that light. Okay. And so this is just some code showing how to define a light. So the first thing is just to define the light source and its color. And then we're going to add it to the scene. So at that point, it would affect every light in the scene, but it wouldn't be movable. It would just be at a fixed location. Not very interesting. The next code is very similar to what you saw in the moving camera example. We're going to create a group node, add the light to it, add that group node to the root, and then we can, using transforms, manipulate the position of that light. So the concept is very similar to cameras. Okay. All right, now we'll show some demos of lighting. Yeah, yes, thank you. So those two spots are actually visual representation of the lights in the world, and we can animate it. So we actually have one of the lights, and we literally have created a group node with some geometry representing the light and a light node. So it's a group node with two objects there. And then as we move that group node around, not only does the position of the light that you see changes, but its effect, if you notice that it now illuminates the objects differently as it goes around, just like a real light would. And then in the upper right-hand corner, we're animating the color of that light. And so it's changing from green to white and back. All right. Now we'll go to where we're going to talk about materials. So far everything just looks like a white blob. It's shaded, so you can tell it's got some 3D-ness to it, but it's not very realistic or very interesting. Materials are the way you add an appearance to your object to make them look more realistic and more interesting. We define in JavaFX 8 one specific type of material. It's called a Phong material. For any of you who are familiar with Phong lighting, that's where that comes from. So our material contains the following properties. We have an ambient, diffuse, and specular color. More interestingly, for diffuse in particular, we can define a texture map. That it's an image that will get mapped onto your object to give you either a picture that's wrapped around your object or an interesting pattern, and we'll show you an example of both of those. And then we have a few other things. We have bump mapping, which we can show you. Like geometry, this is shareable among multiple shape 3D nodes, so you can create a library of materials and use them in multiple places. Okay, go ahead. You create materials pretty similarly to the way you do everything else. In the interest of time, why don't we go ahead and move on to the demo? And so what we're going to do here is, this is the same demo, but we're going to show putting, first of all, just a flat image on there. So we're going to put a diffuse map on there. So you can see that's got a little bit of things. And now maybe you could switch to the other primitives. So we've got a little different image. Oh, that's not the right one. Right. No. Okay, so if you look, so go ahead and put the image back on there. So again, this is a just a texture that we've created for this, but it looks pretty flat. So that's where bump mapping comes in. And so now if you turn bump mapping on, no. Yeah. So if you turn bump mapping on in addition to the texture, we've got something that looks a whole lot more realistic. And so we can show the bump map and the texture independently. Or in this case, we've got a different map. So again, we've got a nice little textured pattern on here, but it actually looks like it's got some texture to it that's not just a flat image on there. And then the box is an even better example of that. So if we switch to the box, so that this one's interesting. If you turn bump map off and on, but leave the texture on the whole time. So if you turn bump mapping off, it has a very different, no, wrong one. Yeah, there you go. So it has a very different look to it. That looks very flat, even though it's a nice image. And then if you turn it back on, you can see it actually looks properly textured. And so that's all things we're adding. So this is a prototype of what we will be delivering in JavaFX 8. All right. Thanks. All right. So it sounds like there's some interest in the room from us actually delivering on that promise. So that's a good thing. We'll try to keep that promise. So I think that's pretty much it. I think we had a little bit of a wrap up. So about the only other thing we wanted to highlight on the slides is we wanted to run sort of a couple of last little demos. So it's all great when you can define things as easy as cylinders and spheres and boxes. Those are really easy to, even I can write the code for that. I can't write a code for modeling a chair or this room or anything else complex. That requires somebody with some modeling skills and a very expensive piece of software, and then they produce a model. And so you need some way to get that in. There are many popular file formats in existence. There's one of the oldest ones is Wavefront OBJ file format. There's Maya, 3D Studio Max, Collada, KRML, and a number of others. I would imagine as many file formats as you have companies producing modelers. We're not going to provide a standard loader as part of JavaFX. Our file format is FXML. So we will have FXML support for 3D, just like we have for everything else. But we recognize there's a lot of popular files already out there in file formats. And so we want to provide loaders for at least a couple of popular formats. And we're actually going to demo one of them here as sample code, though, not as part of the shipping platform. Okay. All right, so let's go on to the loader demo. Okay, so now we're going to show just a quick example of loading an object. So this particular one is something that our good friend Kirill had one of his good friends generate. This is a model of a chair or a sofa. And like I said, this is something that I doubt there's anyone in this room that could come up with a mathematical representation of that object. But it actually looks pretty realistic because in addition to having the geometry modeled with a modeler, you can see there's realistic looking textures with bump mapping on there. And so we've got both the wood grain and the fabric. And that's all rendered using JavaFX prototype in real time. And then for one last demo, we're going to end with a demo of it's like a prototype of an application used for shipping containers. So if any of you saw the keynote demo, I believe the actual application, this was Navis is the company that does this, the actual application was shown there. We're just showing a prototype demo version of that here running live. But you can see we have 3D picking. That was one of the things we alluded to earlier. And then you can change the appearance. You can move the camera, change the appearance down there on the lower left. So we can highlight things based on how perishable they are, and you can get stats by clicking on them. And so this is just an example of something you could actually do a real app with JavaFX. Right, and then you can see we can switch to a more 2D view as well. All right. Anyway, thank you all for your attendance, and I didn't leave quite as much time for questions as I'd hoped, but we've got about 5 minutes.
Yeah,
Oh, go ahead, Carol.
yeah, I want to add one thing that modern video cards does computation very well. For example, it is feasible to have 1 million face models in real time.
Right.
So it is even feasible
On this laptop. All right, so we're expecting it'll be a pretty powerful thing. Yes?
I see why you need to have pixel shaders. You use shaders?
Yes, we even for 2D we do. And actually everything you saw here makes heavy use of it. So even our 2D pipeline uses pixel shaders. Not at the user application programming level, we use them internally. So when you define a bump map and a diffuse map and all of those maps and the lightings, we do per pixel lighting using a pixel shader in this prototype, and that's what we're going to do. Actually, there are a lot of challenges in doing that. We can maybe chat about that at some point, but the main challenge is we're already using them for other things, and what language would you use? So those are the two big challenges. So we don't plan to do that in this release. Any other questions that haven't been answered already? All right, well, thank you, everyone.